course, make it worthwhile for everybody involved. People, this is an extremely important course, right? It's called Deep Learning, and it's a core part of AI because it's core because what's really happening is that, all right, how does self-driving cars work? How do self-driving cars work? What do self-driving cars use? What technology do they use?
LiDAR.
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 The first thing that comes to your mind is LiDAR.
Cameras.
Okay, first thing should be cameras. Cameras. I have a dash cam in my. What about cameras?
Vision.
Computer vision. Computer vision. Right? Computer vision is what we're studying here. So it's the future, right? Airplanes. Airplanes. Currently, they probably don't use a lot of computer vision, but when airplanes start to land themselves, what do you think they're going to use? Yeah, there will be some LiDAR involved. What do you think is mostly going to be involved?
It's going to be the same computer vision. Cameras.
You're trying to give trouble? You're trying to give me some trouble, you know? Eh? He's trying to give me trouble. By the way, I love that shirt. I need to borrow it. We're going to talk about it. Even though I just told somebody upstairs that I can't take, he brought, very nice guy, very, very nice guy. I like him a lot. He brought me some muscle milk. All right, people, let's talk about this code. So basically, if you go into Canvas, I've did some reorganization, right? And basically, you know how module 3 and module 4. Module 3 is a theory, right? Including a little PowerPoint that I put together. You people love PowerPoints too much. Anyway, I put together a little PowerPoint, kind of summarizing it. But basically, these are some stuff I've been working on, right? All colors are represented in a picture, right? Maybe I can just bring up, maybe I can just bring this up. AUM teaching 6550 module 3. Our colors are represented in a picture. I don't know. I mean, it might make it a little bit clearer, as well as maybe not. I don't know. But yeah, look at them. And you know, of course, I'm sticking to the India theme. You people came from very far away. So I have to show you that I appreciate you, right? That's why I indulge you people a lot, you know, talking about India and Indian movies and all of this type of stuff, right? So you guys know that, okay, all right, I appreciate you guys coming so far, right? All right. Here's a picture, break it down. This is basically your Indian saffron, Indian green. And then you have the 3 layers. The thing has 3 layers, right? You have a red layer, green layer, blue layer. There's a little link you can go to look at screen printing. This is a video about screen printing, how to screen print t-shirts. Basically, it shows you how they have these 3 screens and they run the colors through the screens and it applies the color to the t-shirt, right? So you have the red layer, green layer, blue layer, and in the red layer, you have the, you know, 255, 255, 255 is actually white, right? Right? So you can represent 60 million colors in a picture, right? 255 is the full red. 4 is a teensy bit of red, right? What you find, oddly enough, in these things is that green is probably not what you thought it was going to be. 02550, this is actually raw pure green, and this is raw pure blue. It's not quite what you thought it would be. Navy blue is actually only 141 out of 255 blue, right? Yeah, it's the oddest thing with these colors. And then we talk about pixels, and then I talk about how you flatten images on a CNN, right? you know, you take the red, this is just a red layer only. You have AUM 7x7 pixel, 7x7 pixels, and you have different numbers representing each color for each pixel. And then you flatten it, right? Pixel 0, 0 down to pixel 6, 6. Remember, we start counting at 0, right? And then you have input and output layers that talk about the output layer, right? In a neural network, understanding convolutions and max pooling. You have your input. Oh, well, that's max pooling, right? And then up here you have convolutions. You have the kernel, and you're moving the kernel across the image, right? For the sake of clarity, let's say, okay, in this case, we're using a 3x3 kernel. So in other words, it's covering 3 pixels across, 3 pixels down at a time. You can move it 1 across, which is a stride of 1, or 2 across, which is a stride of 2, or 3 across, which is a stride of 3. And then all you're doing, you know, is remember, you're just multiplying this times that, that times that, that times that. You're multiplying the pixel that the kernel covers, right? So this one covers this one covers one covers one, 0 covers 0, 0 covers 0, 0. Sorry, 0 covers 2, 0 covers 2, 0 covers 2. Minus 1 covers 3, minus 1 covers 3, minus 1 covers, right? So you're doing what they call element-wise matrix multiplication, right? Instead of across times down, across times down, across times down, what you're doing is that times that. You're multiplying by the element in the same location, right? And this is what the calculation looks like. And you get this. Then you have max pooling, and all you're doing is you're moving the kernel across. Take the biggest value, 8. Uh-oh, made a mistake here. You people supposed to look at these things and tell me if I have a mistake here, right? So this is actually 8. Right. Anyway, so you get the idea. Move it across 2 again. You get 12, right? Move it down. You run out of space, you move it down. Biggest is 15, etc., 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 right? So you can look at these little things. Dropout layer. We're just turning off pixels, and then the signal from the pixel just doesn't kind of you know, count. And then what are we looking at here? X-train and X-test, Y-train and Y-test, right? Just showing you kind of how we break it down, right? How it becomes X-train, X-test, Y-train, Y-test, right? This is how it should look. All right. All right. Anyway, so let's look at hyperparameters. So basically, so we have this code. And so by the way, you also have this, I did this little PowerPoint for you, right? Which summarizes the different parts of the new convolutional neural network. Now, remember, convolutional neural network deals with what types of data? What type of data do we process in CNNs? You guys don't know? What type of data are we processing? People, if you can't answer this question, might as well stop right here and go have lunch. What type of data are we processing in CNNs?
Structured.
Opposite. Unstructured, right? Specifically, what type of unstructured data? We're talking about it. Computer what? Vision, right? Which deals with what?
Image.
Images, pictures. Images also known as pictures, right? All right. So I have a little PowerPoint that I did for you. And basically, you know, so we have a summary of the different parts of the CNN, right? That you can kind of go through, right? All right, now in module 4, we're looking at hyperparameters. So understand something, understand what's going on here. We saw where each neuron does an individual regression with the formula Z equals WX plus B. Everybody remember that? Yeah? Y'all got 100% in quiz 2, you know. So if you're not remembering this, if you're not understanding this, that's a problem, right? All right, very cool, very cool, right? No, so we said Z equals WX plus B. That happens in every single neuron, right? In every single neuron, you have Z equals WX plus B, right? And then it happens all over again in the next layer, right? You have your input layer, you have your output layer, right? This is an input layer with 5 features that I'm pointing to here, right? You have an output layer with 2 categories. And in between, you have 3 hidden layers, right? Each of these hidden layers has something like 8 neurons and then 5 neurons, right? Each of these neurons is doing a formula, is doing a small linear regression, right? With a formula Z equals WX plus B, right? Similar to Y equals MX plus C, right? Very cool. Now, so what I want to say to you is this. The same neural network that you use for structured data is the same neural network that you use for unstructured data, right? All you're going to do is you're going to take out the max pooling and the convolutions, right? All right, let's look at hyperparameter tuning. So I mentioned this Z equals WX plus B because these parameters are learned by the network, right? W and B. It learns these parameters throughout the network, right? It learns the parameters throughout the network. And these weights are really what constitutes what the network learns. It learns the relationships between these inputs, right? And these outputs as represented by Z equals WX plus B. So it learns W and B. Knowing the relationships between W and B helps it to predict, helps it to take these 5 inputs and know what these 2 outputs should be. Bearing in mind that these outputs are 2 probabilities, right? The first one is the probability of the first category. The second one is the probability of the second category. Bear in mind that probabilities all add to what value? All probabilities add to? No, to what? All probabilities in a given situation add to what? Add to what value? No. To what's the second one you said?
0, 1.
Well, 1.0, right? Remember, all probabilities add to 1.0. So this network is nothing but a bunch of weights, right? W's and B's, right? That are learned between the layers, right? Right? And remember, each neuron connected to every other neuron represents a W and a B, right? All right, so we're learning these parameters, which represent the weights of the network, right? Right? And these represent the weights, right? So every neuron, every connection between 2 neurons or inputs / outputs is a parameter that is learned. Remember, we learn these parameters by propagating the data through the network in a process called feed. Feed what? Feed backwards. Feed backwards? No. Feed what? You guys, everybody in here now got between 80 and 100% on quiz 2. And it was supposed to be a learning quiz. I noticed a lot of you got 100% the first time. And some of you took 5 minutes to do it. We do feed forward, right? We feed the data through the network. We take these input values, right? We feed them through the net, all the layers, and we get outputs in the form of probabilities, right? Then we do back propagation, where we take the loss, right? The loss, which is the difference between the predictions and the actual labels, and we feed it back through the network in a process called back propagation, right? Backward propagation, or back prop. And over several epochs, an epoch being the process of feeding all the data in the data set. When we feed all the data in the data set through the network, if we have 50,000 rows and we feed the 50,000 rows through the data set, that's called one epoch, right? It learns the relationship between the inputs and the outputs. And those relationships take the form of weights, right? Right? So like we said, we feed the data into the inputs through the hidden layers. We get outputs. We take the difference between the outputs, right? The predicted outputs and the actual values. So for example, if these pixels were from a cat, and it says that it's a 90% probability that it's a dog, then we have a high loss. And we'll feed that loss back through the network to adjust the weights. Yeah? And after doing that for several epochs, we should get to a point where most of the predictions for dogs, the pixels for dogs, come out saying that it's a high probability of a dog. And the most of the pixels representing a cat should end up with a prediction, right? That it's a high probability of being a cat, right? All right, very cool. This is a quick review of what we've been doing. So we're learning parameters within the network, right? The parameters are the W's and the B connecting every neuron to every other neuron, right? And so right? Right? All right, very cool. And so, for example, in this neural network, we have 3 inputs, we have 2 outputs, right? We have the 3 inputs connected to four neurons. How many weights are we calculating here in this layer? 3 neurons connected to 3 inputs connected to 4 neurons. How many weights are we calculating here? Let's see if we're understanding anything or we're just spending time. How many weights are being calculated here? 3 inputs, 4 neurons. How many weights? Eight. Let's try that again. 3 inputs, 4 neurons. How many weights? We said that every connection between an input and a neuron or a neuron and an output represents a weight, right? So from this layer, the 3 to the 4 is how many weights? 3 to 4. No, 12. From the 3 to the 4 is how many?
12.
4 to 4 is 4 to 2 is
8.
all right, beautiful. All right. Right? All right, beautiful. These are the parameters that are being learned by the network, right? Over the course of feeding the data through the network and back propagating the loss back through the network, right? Now, brings us to today's discussion, which is hyperparameters. Hyperparameters are what the scientist controls, the data scientist, the AI specialist controls the hyperparameters. These are the parameters that you use to tune the network so that the network can learn its own parameters, right? So we control the hyperparameters. The network learns parameters, right? We can't control the parameters that the network learns, right? What we control is the hyperparameters. So let's look at some hyperparameters today. So let's start with, so we talk about, so the first major thing we can control is the size of the images, right? Now, remember in this case, for example, CFAR is 32 by 32 pixels. This doesn't compare very favorable to a 1 megapixel picture. A 1 megapixel picture is how many pixels times how many pixels? 1 megapixel, mega equals, mega means what? People, we can't learn data science. We can't learn AI and deep learning with this energy level. What we're doing here is babysitting. Mega means, mega means what? Kilo means what? Mega means? No, mega means what? Million, right? Right? Megawatt is a million watts, right? Megabytes is approximately a million bytes, not quite a million bytes, right? So a megapixel picture is 1,000 times 1,000. Everybody say that? Yeah. So if we condense the picture down to 32 by 32, that's not a lot. It's necessary because the compute required to process a megapixel picture is huge. Yeah. Now, when you sit in front of your laptop and your camera or your smartphone and it takes a picture, right? It's taking a megapixel picture. It's most likely condensing it down. But even so, you're talking about one picture. You're not training it on 10,000 pictures, right? All right, very cool. So larger images have more details. It's easier to classify them, but the computational cost is tremendous. So the first thing we have to control is the image size. Not just the image size, but the number of colors in the image. Remember, a regular image is 256 by 256 by 256 pixels, right? I mean, colors, which is 16 million. Now, there's a data set called MNIST. MNIST is there's a fashion MNIST. There's a fashion MNIST as well as numbers, right? And to make it more manageable, I'm not sure. This might just be black and white, right? Okay. So the color depth is another important. Now, image size and color depth is not really a hyperparameter, but is the single biggest thing that's going to control the quality of your classification. Now, by the way, if you have a lot of time to do your classification, then it's fine to use bigger images. But aside from the time it takes to train the model, there's also the time it takes to do the prediction, right? To do what we call sorry, not prediction, what we call the word is slipping me right now. It's called when you use it in real life, it's called I'll tell you in a second. All right, so that's the first big thing you can control. Now, structured data. So for example, if you were processing some structured data on loans, who is a good credit risk, who is a bad credit risk? And you have things like credit score, salary, years at current job, age, salary, assets. This is all numerical data, right? This is what we call structured data that you would find in a table. Yeah. If you're doing a regular neural network, in other words, not CNNs, not a convolutional neural network, then the issue of images wouldn't apply, right? All right. Now, first big hyperparameter is the number of layers in your network. Number of layers in your network. Here we have network with 2 hidden layers, right? With hidden layers. Here we have a network with 2 hidden layers again, input layer, output layer, right? 2 hidden layers, right? Hidden layers, number of hidden layers is the first big thing you want to think about. How many hidden layers will you have? The more hidden layers you have is the more features you can learn. The more complex the pictures is the more features you can learn. Now, remember, for example, that in this first hidden layer, you might be detecting things like edges, right? You might be detecting things like edges. In the second hidden layer, you might be detecting things like shapes, wheels, eyes, nose, mouth, wings. Yeah. So the more layers you have is the more complex the features you can detect, right? But there comes a point where there's what we call diminishing returns, right? Meaning that adding more layers doesn't add to the accuracy of the model, right? All right. So second thing is the number of layers. Now, if we jump over to here, by the way, if we jump over to here, this dense is a hidden layer, right? Or they may also call it a fully connected layer, right? Fully connected because of this. See, one neuron is connected to all the other neurons in the next layer, right? One neuron to all the other layers. So so you might call it, you might hear it called fully connected layer, right? You might call it, you might hear it called a dense layer, right? It's called dense here. Might be called fully connected, or it might be called hidden. Yeah. Now, so you have the number of layers and you have the number of neurons in each. This is 512 neurons. We have 512 neurons in this hidden layer, right? So that's the next big thing. The 2 next big things you can think about is number of hidden layers. In this case, how many hidden layers do we have in this code? No, but look again. Is it 3 or is it 4? How many hidden layers do we have in this neural network, in this CNN? 2? 2? Why you said 2?
There's only dense twice.
You said dense twice. Yeah. Correct. So 2 dense layers. Correct. Yeah. Now notice this one is the output layer because it says num classes, right? Num classes in this case is the 10, right? Remember in CIFAR we have 10 classes, right? So we have one hidden layer with 512 and then another dense layer with a number of classes, which is actually the output layer, right? All right, very cool. Now, this is where a lot of the computation is going to be taking place in these dense layers. And so it's going to affect the time for each epoch. Remember, the epoch is when you feed all the data through the network, right? So a lot of the time is going to be taken up in the dense layer, right? Because remember, 512 means that you have, for each of these neurons, now, for example, what this is saying here is that the flattened layer, flattened turns the 3 by 3 by 32 into 288. So really you have 288. How many calculations do you have between this flattened layer and the dense layer? How many calculations is that? How many calculations? Remember, you know, the dense layer is connected to all, each neuron in the dense layer is connected to each input. So how many calculations are we talking about here?
147,000.
All right, let's see if you're right. Now, to be safe, you want to just say 288 by 512, right? Which turns out to be 147,000. Correct. Cypreet, I think you're ready to teach this class. You're doing really good. People, I need the energy level of Cypreet. Sitting in the courses, sitting in the class is one thing, you know, doing it, participating, being active, being energetic about it. That's what you need, right? That's what's gonna bring you success, right? All right, very cool. People, it's competitive out there, no? You can't be just kind of sailing through. Gotta put yourself in the driver's seat, right? So what we have is 147,000 calculations, right? It's 147,000 calculations. That's this parameters here. Yeah. That's these parameters that's being calculated. 147,900 and, well, 968. What do you think is the difference between the 147,456 and the 147,968? Well, I'll show you. Equals that minus that, right? 512. What do you think this 512 represents? All right. So this is W, and this is bias, B, right? Correct. So what we're saying, people, what we're saying is that out of the 181,162 parameters that are calculated, 147,000 of them are calculated right here. That's the W's, right? Plus another 512 for the bias, right? So the point is, the compute, most of the compute is spent here. Yeah. All right, very cool. Very cool. So second and third, 2A and 2B is the dense layers. How many dense layers and how many neurons in each? Now, it says here, structured data uses fewer layers as complex hierarchical features are needed. So what we're saying is, if you're simply calculating who is at bad risk or who's at good risk for a loan, right? You're not calculating things like edges and shapes and wheels and eyes and mouth and nose, right? In the thing. So therefore, you're gonna need less neurons in your dense layer if you're doing structured data, right? All right, let's move on. Right? All right, sorry, yeah. So fewer layers, right? Because we don't have these, what we call a hierarchical thing, right? We don't have the hierarchical thing where we're doing edges, and then the edges combine to make shapes, and then the shapes combine to make features like eyes and nose and mouth, right? So we have fewer layers in the case of structured data. But we have more neurons per dense layer. Yeah. Right. So in other words, for structured data, you might have another dense layer. Sorry, you might so for CNNs, you might have 2 or 3 dense layers, right? But for structured data, you're gonna have even more. You might have 1024, you might have 2048. Notice that most times this is they do this in powers of 2, right? For some reason, powers of 2 work best. Yeah. All right, very cool. All right, convolutions. In the case of structured data, we don't use convolutions, right? So in other words, in the case of structured data, this drops out, right? This drops out and this drops out. Cool. So all of this is unnecessary for structured data or numeric data. Cool. All right. When the case of convolutional neural networks, the first big thing to look at is your kernel size. So notice here you have a kernel size of 5, 5. Right? 5, 5, which means that for a 32 by 32 image, right? The kernel would look something like so basically you have sorry, let me see if I can bring this up. All right, so here we have a 3 by 3 kernel, right? In this case, we're using a 5 by 5. This illustration has a 3 by 3 kernel, right? 1, 2, 3, 1, 2, 3. Here, we're using a 5 by 5 kernel, right? The stride is 2, 2, meaning each time we'll move it across by 2, 1, 2. And then we'll do the multiplication again, what we call element-wise multiplication. Yeah. Right. Now, padding. Now, padding might be necessary because what happens with these kernels is that you lose information. Notice that every time you multiply, you're losing the information on the edges, right? You only really get the information when it's in the center. You get all the information when it's in the center. So you may add zeros at the end. So it looks something like this, right? So you pad the image with zeros around. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, etc., right? Uh-oh. You add zeros around the image, and that preserves more of the information. Otherwise, you kind of lose information on the edge of the image, right? So padding same simply means that you can specify a number, but padding same means that you retain the image size, right? You retain the image size, right? All right. Now, after that, we have an activation layer. I remember we talked about activation layers. We talked about the activation function. Remember we said that you can have several types of activation functions. You can have ReLU. What's another activation function we have? Sigmoid. Leaky ReLU. And what's another one? And tanh, right? So in this case, we're using ReLU. We tend to use ReLU for convolutional neural networks, right? But in the case of structured models, can be ReLU, can be sigmoid, leaky ReLU, etc., right? All right. So that's this activation. Now remember that you have the, for each neuron, you have Z equals WX plus B, right? Representing the regression, and then activation A equals G times Z, right? The activation function times Z, right? So whichever value this is calculated, whichever value is calculated here, the activation gets applied to it. And right? And then in the case of ReLU, all that's happening is that if the value is negative, it gets chopped off, right? So if the value is negative coming in, it gets chopped. But if it's positive, it gets transmitted. That's all that's happening, right? So that's your, that's the next, that's the next, that's the next, that's the next, that's the next. That's the next. That's the next hyperparameter. Yeah, so we tend to stick with ReLU for convolutional neural networks. Whereas in the case of structured data, right? Tabular data, take the data from a database, right? We might have sigmoid, we might have leaky ReLU, etc., etc. All right, next we have the max pooling layer. We have the max pooling layer. Right, we talked about kernel size, stride size, and padding, right? Next is the max pooling. Max pooling does what we call downsampling, right? Now, what it does is it captures the essence of the feature. So remember, your convolutions are doing, remember your convolutions are doing feature detection, right? You have horizontal edge detection, vertical edge detection, etc. Then the max pooling extracts the most significant features that are detected, right? And it does what we call downsampling. So this in this particular case, this 4x4 image gets downsampled to a what? To what? To what by what? Nobody can. Wild guess. Somebody take a wild guess. This 4x4 image gets downsampled to a 2x2. People, I'm not here to trick you, embarrass you, or make you feel stupid enough. I literally just wanted to participate. I'm literally not trying to set any traps for you. Right? And what? Young lady, why are you on your phone? Young lady, why are you on your phone? Why are you on your phone? Come on, you can't do that. All right, now, here's why this downsampling is so important. Remember that without, okay, so we have these two convolutions, right? And we have this downsampling. Now, without this downsampling, we wouldn't have 147,000 parameters to calculate. We would have a lot more. Yeah. So the downsampling reduces the computation required, right? Downsampling. So downsampling, it comes from a concept of, so for example, in CD production, in music production, we have analog signals, right? And what happens is that when you're making a CD, it samples the music. It samples the music, right? It samples the music at certain intervals, right? So let me show you something. So you have this sine wave, which represents the music. I don't know if you remember your physics, right? You have the sine wave representing the music, right? Right? And really what happens is that with downsampling, what happens is that, so this is analog. Analog looks something like this, right? Analog looks something like that. With downsampling, what we have is we sample slices of the image, right? Right? We sample slices of the image, right? At different intervals. And we digitize the value at that interval, right? Yeah, stuff is getting better and better, right? Right? So instead of continuous values, as you would have in analog, what you have is sampled values at intervals. Same thing happens, by the way, in your cell phone. When you're talking on your cell phone, what's really happening is that it's sampling your voice, right? Sampling your voice at intervals, converting it to a digital signal and transmitting that digital signal down the line. Yeah. And that makes the whole, makes the processing more manageable. It reduces the bandwidth required to send your voice, etc., right? So that's max pooling. It does the downsampling. Okay, very cool. And in the case of structured data, we do not need this downsampling, right? All right, very cool. With max pooling, we have the kernel size. Again, though, we can set the kernel size. The bigger the kernel, let me ask you something. If we wanted to downsample, if we wanted to reduce the size of the image more, what would we do with the size of the kernel? Huh? All right. In other words, if we set this to 3, 3, if we set the pool size to 3, 3, is the output going to be bigger or smaller? It's going to be bigger. You said bigger. Anybody else? You're changing it to smaller because I say anybody else. It's going to be smaller because remember, you know, with max pooling, you're doing this. You're taking 4 and you're taking the maximum of that 4, right? If it was 3, 3, then you're taking 9 and you're summarizing it down to 9, right? So in other words, and then if it's 4, 4, so in other words, if it's 2, 2, you get 8 here. Oh, didn't change it, right? This goes from those 4 to 8, those 4 to 12, etc., etc. If it's 4, 4, then how many values do we have here? And what's that value? Huh? If it's 4, 4, if the kernel size is 4, 4, how many output values do we have? Huh? 1. 1. Because we're taking, because this becomes our kernel, right? And then the whole kernel covers everything, right? Covers everything. And then we're taking the 1 maximum value, which is what? What's the maximum value in all of this? 15. So it downsamples it to 15, 1 single value. So in other words, the smaller the kernel, the bigger the output, right? Smaller the kernel, the bigger the output. Now, notice that not just the size of the kernel, but also the stride, right? Because when if you have this 2x2 kernel, all right, let's take this 3x3 kernel. If we move it by 1 across each time, then we're producing more values, right? If we move it by 3, then it goes from here, we're producing 1 value here, right? Move it over to here, producing 1 value again, right? But if we have it here, produce 1 value, second value, third value, fourth value, right? So 4 values. So the stride also affects the downsampling, right? The length of the stride also affects the downsampling, right? Bigger the stride is the greater the downsampling. The bigger the stride is the smaller the output. All right, very cool. So that's max pooling and convolutions, right? Again, remember, models with structured data don't need max pooling or convolution, right? Activation function. We talked about activation function already. Let's talk about dropout rate. Remember, dropout rate is a way of controlling over what? Well, it starts with F. Starts with F. Overfitting, right? Overfitting is when we fit the data, fit the network to the data too well. We'll fit the data to the network perfectly, but when we try to predict values that we haven't seen in the training data, it's going to perform poorly, right? It's going to perform poorly. It's going to perform poorly, right? Going to perform poorly. So overfitting is a type of regularization. And what it does is it makes sure that we come out with the broader patterns, the bigger patterns within the data, right? It doesn't fit the data super specifically, right? So the accuracy on the training data is going to be a little bit less, but the accuracy on data that you haven't seen before is going to be better, all right? It's like, for example, if I say, all right, what is your, if I say, okay, what's your favorite meal, right? Now, all right, what's a favorite meal of, what's a favorite meal in Telangana? Biryani, right? All right, very cool. I say biryani all the time, right? There's this movie where the guy, he's a police officer who, it's a police officer, it's Indian movie, right? About police officer who investigates missing woman. Yeah, this one actually. And in it, the guy above him insults him by sending him to go get 2 biryani. Treats him like an errand boy, right? In this movie, he's investigating a missing girl, missing young lady. It's a missing young lady, not missing girl. So yeah, so anyway, so at one point they insult him and they send him to go buy some biryani, right? Actually, one of the in that movie, there's a funny part to the movie where the guy who reports to him, tells him, "Sir, give him a tight slap," right? Tight slap is one of those funny Like every time I hear somebody say, "Give him a tight slap, sir," I just find it very funny, right? Tight slap. Yeah, very good movie. I think it's on Netflix too. Yeah, actually, Netflix is where I saw it, right? Yeah, yeah. Actually saw it on Netflix. So the guy insults him. His superior officer insults him by telling him to go and fetch 2 biryani, right? Anyway, all right. So anyway, the point is that you could say, okay, what type of biryani? What type of biryani? What type of biryani? Chicken, right? All right. How many said chicken? Hands up, people who said chicken. Hands up who prefer chicken. 3, 4. Hands up who say mutton. Hands up for mutton, right? All right. So chicken. How do you want the chicken biryani? How do you do it? Oh, you want it super spicy? Super spicy, right? What? All right. What spices you want in it? Huh? What spices? So the point is, if I was to study you guys, right? And you guys not, well, I don't know. Only six of you like biryani. Goodness gracious. What's wrong with the energy level? What's with the energy level? Imagine I'm 55, right? And I'm half sick. And I have more energy than you guys. What's going on with you guys? All right. And I'm not a morning person. I hate mornings. All right. Anyway, so the point is that you can learn the taste preferences of a group so well, so accurately, that you can get exactly what the people in that group want. But if you were asked people from the north, then they're going to say, what's the favorite food in the north? Places like, say, Gujarat. Huh? Roti, right? So this is what it's like, right? You have a wedding. Right? Like if you watch this movie, what's this movie I just saw? I went to see this movie and I was so disappointed. I didn't see any of you guys. Nila Vuku, I think it's a Tamil movie. Yeah, Nila Vuku. Not one single one of you guys. You guys only watch Telugu movies, right? Why you don't support other people's movies? Huh? What? You watch Tamil movies? Just like me? Dhanush and Anika. Actually, I want to be like this guy in this movie. Eh? Huh? Dhanush is the director for that movie. Dhanush is the director. Oh, he's also. Oh no, he wasn't the star. Who is Prabhu in the movie? Isn't the guy called Prabhu? No? No, the guy was called Prabhu. Yeah, I think the guy is called Prabhu. Anyway, all the women in this movie love Prabhu, right? All the women in this movie love Prabhu. I want to be like Prabhu, right? Anyway, all right. It must be Pavish. Anyway, but you get the idea. All right. So let's finish up. So dropout prevents overfitting. Overfitting is where you learn the patterns in one specific set of data extremely well, but you're unable to make good predictions from another set of data, right? You can't make good predictions from another set of data, right? And we said that dropout is one way of fixing this. Early stopping is another way. Because in other words, when you train the model for many epochs, then again, it gets overfit on the data. Wait, hold on a second. All right, who's in trouble out here? Who's in trouble? Nobody? Okay, very good, very good. Nobody's in trouble. All right. All right, we just have a few more to go. Optimizer. So the optimizer is what controls gradient descent. Remember, we talked about gradient descent, and we said that gradient descent is where, right, is where essentially you have the model, and as you feed the model, as you feed the data through the model, right? As you feed the data through the model, it reduces the loss in the model, right? So it measures the loss between the predictions and the actual labels, right? Right? And it reduces that loss. Now, reducing that loss is called gradient descent, right? Because what is happening is that it's reducing the loss. Now, it's very important to understand something. As we reduce the loss, we reduce what's called the learning rate. The learning rate is the rate at which we reduce the loss. Wait, hold on. Hold on, one second. Right. Okay, yeah. So remember, the loss is the difference between the actual predictions. The loss is the difference between the predictions and the actual labels, right? All right, very cool. Very cool. So in real life, it looks something like this. You have, let's say we have three categories, right? We have dog, cat, horse. Right? Dog, cat, horse. Now, what we call the ground truth label. Ground truth label, meaning, so you have these pixels, right? You have these pixels, right? Right? And what you want is for it to say it's an actual, that it's actually a dog. So what you want is for it to produce 1, 0, 0, right? Yeah. This is a dog. This is a picture of a dog. So you want it to produce 1, 0, 0. No, it may predict, the actual prediction may be 0.3, 0.4, 0. What? Remember, predictions, probabilities must add to what? 1, right? So what's the loss? The loss is that minus that, right? Right? And it's the sum of all of this. Right? Because 0.7, 0.4, 0.3, right? So the loss is actually equal to the sum of all of these. Now, this is not the actual formula. The formula is a lot more complicated than this. But the idea, but this is the idea, right? No. So this is the loss, right? Now, when we get the prediction looking like this, 0, 0, then the loss is equal to that minus that, right? So we have, right? Right? And the sum of that loss is 0. Everybody with me? All right. No, the calculation doesn't look like this. This is a very, what we call brute force representation of what the calculation actually looks like, right? But the point is, as we feed the data through the network, we're adjusting the weights so that the loss goes to 0, right? It's not ever going to get to 0, right? But the idea is we try to adjust the loss so that it creates the predictions that are accurate. Okay, one last thing, or two last things. Learning rate. So the learning rate is a rate, is a number, learning rate, also known as alpha, right? Is the adjustment to the loss that we back propagate through the network, right? All right. I'm trying to reach Nitya or Naya. Yeah. Try to reach Naya, right? I'm trying to reach Nitya, right? Now, let's say I ended up at Navi, right? So the loss is 1, 2, 3, 4, 5, right? The loss is 5. Now, no, this is not what I'm going to do. I'm not going to take away 5 so I can get to Nitya, right? Because that's going to make me bounce back and forth, right? What I'm going to do is I'm going to take away a percentage of that loss, right? So let's say I use what we call a learning rate of 0.2, yeah? A learning rate, all right, let's do it this way. Let's use a learning rate of 0.4. The loss is 5. The distance between where I should be and where I am is 5 spacing, right? I'm going to use a learning rate of 0.4, right? 0.4 times 5 gives me 2, right? So 1, 2. Now I've reduced the loss. Good. Now, here's what happens next time. I'm going to reduce that learning rate. This time I'm going to use 0.3, right? So now the loss is 1, 2, 3, right? Right? So 0.3 times 3 is going to give me 1 space over, right? Then I'm going to reduce the loss, the learning rate of 0.2. Now the loss is 1, 2, right? So 2 times 0.2 is 0.4, takes me halfway. What I'm going to do is very, very, very slowly approach it here, right? Now, if I say the loss is 5, so I'm going to minus 5, what will end up happening in reality is that I keep bouncing all over the place, right? And we'll explore this more, right? But the idea is that we slowly reduce the loss to approach, we slowly reduce the loss by the learning rate, yeah? So when we back propagate through the network, we're going to adjust the weights so that it takes us closer to where we want to be, yeah? And we're going to actually reduce these steps, make them tinier and tinier until we just barely reach it. Sure. Right? Otherwise, we're gonna keep bouncing. I'm gonna come back to 90. We're gonna keep bouncing, right? You will see more of this and how it actually works. But this is gradient descent. And so, like we said, we have this learning rate, right? Where we reduce the loss and we keep going down the gradient, right? Now, one last thing is what we call the gamma. The gamma is the rate by which we reduce the learning rate each time. All right, that's all the time we have. Let's take some attendance. Let's take some attendance. You've been a good audience, mostly. Didn't realize we'd run out of time. All right, Priyanka, Bharat, Hemant, Ajay. Hemant, Ajay, Sai Srikant, Ajay, Nihant, Gopi Bharat, Benarji, Navya Sri, Manikanta, Neeraj, Naveen, Shivani, Sai Jayanka, Babu, Manish, Nitya, Gautam, Naveen, Arvind, Sanjana, saw her, Sayakil, Chandana. Sayakil? Chandana? Saipreet is here.
Professor Chandana.
Danny, Shankar is here. Rohita, Himateja, Anurag, Anusha, Pramita, Yeshwant, and Dinesh. All right, see you guys Wednesday. Wednesday we start playing with the network. I'll start running.
So this one, deal with your tea, whatever she says is. Deal with your tea. Anyone ask your.
We literally eat it at 11 o'clock, 11 p.m.
11 p.m. And we still
responded.
responded to him. That's the time. The next day we just finished.
తను లైక్ సబ్మిట్ చేశాను అంటే నేను అన్నాను వాళ్ళకి మెయిల్ చేయు ఇట్స్ ఫాల్ట్ కదా వాళ్ళు ఏమైనా చెప్తారేమో అని తనకి చెప్పాను తర్వాత తను రెస్పాండ్ అంటే లైక్ రిటర్న్ లో ఏదైనా సొల్యూషన్ దొరికింది అని చెప్తే ఆగేవాళ్ళు
He is smart. He wants his grade. He is doing things to get his grade. Okay. You are. I'm not.
Wait, madam, I'm the one who submitted the assignment first, madam. After that, I received mail that our questions are wrong.
Yes.
I mailed you in the evening.
And then he
They all submitted. They are all submitted before 11.
But we don't know that they are
I
not
know it's
actual
okay, but
questions.
No, but she sent an email. Didn't she send an email
I did send
to
it.
everybody?
I did it to
So
everybody.
you didn't receive an email that evening.
Yes, ma'am. They went to the library and they checked it that they said that
So,
we
but
don't
you
have
get
any
back to us to
knowledge.
tell us you did not find it. No, did you get back to us? Because she sent that day I was feeling delayed.